The carbon sequestration potential of perennial cropping systems, a sustainable solution for climate mitigation. The increasing concentration of atmospheric carbon dioxide is one of the most pressing environmental concerns of the 21st century, contributing significantly to global climate change. While fossil fuel combustion remains the primary driver of CO2 emissions, land use changes, particularly in agriculture, also play a critical role in altering carbon cycles. Conventional agricultural practices, dominated by annual cropping systems, are responsible for significant soil degradation, deforestation, and greenhouse gas emissions. As the demand for sustainable and regenerative agricultural methods grows, perennial cropping systems have emerged as a viable solution for carbon sequestration, offering the potential to mitigate climate change while enhancing soil health and biodiversity. Perennial crops, which include trees, shrubs, and grasses that live for multiple years, provide an alternative to traditional monocultures of annual crops. Unlike annual crops that require repeated tilling and replanting each season, perennials develop deep root systems that enable them to capture and store carbon more effectively in soils. This documentary explores the carbon sequestration potential of perennial cropping systems, presenting extensive evidence, case studies, and data to illustrate their role in climate mitigation. By delving into the mechanisms, benefits, challenges, and case studies of perennial agriculture, this analysis highlights why shifting towards perennial cropping could be instrumental in achieving sustainable carbon sequestration. Carbon sequestration refers to the process by which atmospheric carbon dioxide is captured and stored in plants, soils, and geological formations. In agricultural systems, this process is primarily facilitated through photosynthesis, wherein plants absorb CO2 from the atmosphere and convert it into biomass. While annual crops also contribute to carbon sequestration, their short lifespan and frequent soil disturbances through tillage limit the amount of carbon stored in soils. Perennial cropping systems, on the other hand, have a distinct advantage in carbon sequestration due to their long lifespan, deep rooting structures, and reduced soil disturbance. These systems store carbon in multiple ways: in above-ground biomass, like leaves, stems, and branches; below-ground biomass, such as roots and rhizomes; and in the soil through the accumulation of organic matter. Research indicates that perennial plants can store up to 5 times more carbon than annual crops, primarily due to their ability to build extensive root networks that contribute to soil carbon pools over extended periods. A study conducted by the Rodale Institute found that agricultural soils managed with perennial cover crops and reduced tillage had the capacity to sequester over 1.2 metric tons of carbon per hectare annually. Similarly, the Land Institute's research on perennial grains, such as Kernza, demonstrated that deep-rooted perennials could store carbon at depths exceeding 1 meter, where it remains stable for decades. Such findings reinforce the potential of perennial cropping systems to function as carbon sinks, reducing atmospheric CO2 levels while improving overall ecosystem health. Agroforestry is one of the most effective perennial cropping systems for carbon sequestration, integrating trees with agricultural practices to create productive landscapes that sequester carbon while providing food, fuel, and fiber. Trees play a fundamental role in carbon capture by absorbing atmospheric CO2 and storing it in their biomass and root systems. In addition to above-ground carbon storage, tree-based agricultural systems enhance soil organic carbon through leaf litter, root exudates, and microbial interactions. A meta-analysis of agroforestry systems conducted by the World Agroforestry Center found that tree-based agricultural landscapes sequester carbon at rates ranging from 2.2 to 9 metric tons per hectare per year, depending on climate conditions and species selection. Notable examples of agroforestry systems with high carbon sequestration potential include cocoa and coffee plantations in Latin America, where shade-grown practices under tree canopies enhance carbon storage while improving soil fertility. The Amazon region provides a compelling case study of how agroforestry can contribute to carbon sequestration. Indigenous agroforestry practices, such as those seen in the Kayapo and Ashaninka communities, have demonstrated the ability to store up to 250 metric tons of carbon per hectare in above-ground biomass, rivaling some of the densest forest ecosystems. These findings suggest that scaling agroforestry systems globally could make significant contributions to mitigating climate change while supporting local livelihoods. Perennial grains, such as Kernza, a deep-rooted wheatgrass developed by the Land Institute, provide a promising alternative to annual grains, offering both food production and enhanced soil carbon sequestration. Unlike traditional wheat, which requires annual replanting and extensive soil disruption, Kernza's deep-root system, reaching over 3 meters into the soil, allows it to sequester carbon more effectively. Research conducted by Kansas State University indicates that Kernza-based farming systems increase soil organic carbon by 30% over a decade, particularly in subsoil layers where carbon remains stable for extended periods. A comparative study between perennial and annual wheat systems further revealed that Kernza fields sequester up to 50% more carbon than their annual counterparts due to reduced soil erosion and enhanced microbial activity. Another perennial crop with high sequestration potential is Miscanthus, a bioenergy grass cultivated for its high biomass production and carbon storage capacity. A study published in Global Change Biology Bioenergy found that Miscanthus fields sequester up to 4.4 metric tons of carbon per hectare annually, significantly outperforming conventional maize and soybean fields. Such results highlight the importance of expanding perennial grain cultivation to enhance soil carbon stocks while ensuring food security. Silvopasture, a system that integrates trees with livestock grazing, has been recognized as one of the most effective carbon sequestration strategies in agricultural landscapes. By combining woody perennials with forage crops and livestock, silvopastoral systems enhance carbon storage in both plant biomass and soils. A case study from Brazil's Cerrado region found that silvopasture systems store an average of 25 metric tons of carbon per hectare compared to only 5 metric tons in conventional pasture systems. In the southeastern United States, silvopastoral farms incorporating loblolly pine and improved forage species have demonstrated carbon sequestration rates exceeding 3 metric tons per hectare per year. In addition to carbon storage, silvopasture improves soil health, enhances biodiversity, and reduces methane emissions from cattle by providing nutrient-rich forages. The Intergovernmental Panel on Climate Change has recognized silvopasture as a high-impact strategy for mitigating climate change, emphasizing its potential to offset emissions while promoting sustainable livestock production. Despite their evident benefits, the widespread adoption of perennial cropping systems faces several barriers. One major challenge is the economic viability of perennials compared to annual crops. Many farmers rely on annual crops due to established market demand, subsidies, and shorter return on investment periods. Transitioning to perennials often requires significant initial investments, and in some cases, perennial crops take multiple years to reach full productivity. Another challenge is the lack of research and extension support for perennial cropping systems. While institutions such as the Land Institute and the World Agroforestry Center have made significant strides in perennial crop development, funding for research remains limited compared to investments in conventional agriculture. Policymakers and agricultural stakeholders must prioritize funding and technical support to encourage farmers to adopt carbon-sequestering perennial systems. Climate variability also poses risks for perennial cropping, as prolonged droughts, extreme temperatures, and shifting precipitation patterns can affect perennial plant survival. Developing climate-resilient perennial varieties and improving soil moisture retention strategies will be critical in overcoming these challenges. Perennial cropping systems represent a transformative approach to agriculture that aligns with global climate mitigation goals by enhancing carbon sequestration. Through agroforestry, perennial grains, and silvopastoral systems, these practices have demonstrated the ability to sequester substantial amounts of carbon while improving soil health, biodiversity, and farm resilience. Extensive case studies from tropical agroforestry systems, perennial grains like Kernza, and carbon-rich silvopastoral landscapes illustrate the enormous potential of perennials in addressing climate change. However, achieving large-scale adoption requires overcoming economic, policy, and research barriers to make perennial cropping a viable and attractive alternative for farmers worldwide. As climate change continues to threaten global food security and environmental stability, perennial agriculture offers a compelling path forward. By investing in research, supporting farmers, and integrating perennial systems into climate policy frameworks, the potential of these carbon-sequestering agricultural landscapes can be fully realized, contributing to a more sustainable and climate-resilient future.